Hello and welcome back, everyone. I hope you're doing well on this Tuesday afternoon. So let's get started with today's session. All right, so our agenda for today, we'll cover the rules of engagement. We'll then have the main session, which will be run by myself. We'll then have some Q&A and then close out with some updates and announcements from the ALX team. Right, in terms of our rules of engagement, if you do have any questions, please post them onto Slido. Alternatively, if there are more technical, please put them onto AnswerBase. Chat will be open ad hoc to interact with myself and the tutors. And most importantly, listen, learn, and share. All right. So take a moment to scan the QR code. This will take you straight into Slido. Whereas if you do have any questions, you can post them on there for us to tackle. All right. Great. Cool. Right, over onto the main session. Just going to switch over screens for a second. So welcome to sort of the unsupervised exam prep. Now, the notebook will be shared with you at the end for help. So if you do have any questions or are trying to scribble down notes, don't panic. At the end of the session, I will share this notebook with you so that you can have access to it. The aim of this is to recap some of the fundamental knowledge that you need to tackle the exam. It is quite a theory-based exam, so you do need to understand the theory behind the stuff. There is some code execution along the way, but running the code is one thing and interpreting it is another. So just keep in mind that you will need to look back into some of our previous talks that we've had, this talk and some of the theory as a whole through the course to get it done. The exam is untimed, meaning that you have an unlimited time to attempt it. You do have additional attempts for it as well. So log on, look at the assessment, see what questions you have, and make sure you're putting enough time and effort into it. It is 39 questions, so it is quite a long exam. A lot of it being true and false. There is no notebook required for submission, but you might need a notebook to run and execute some of the code in order to interpret what's happening. All right, cool. So looking at your clustering algorithms. So k-means clustering is your most popular algorithm, mainly for its simplicity of use, and you are then able to navigate through that. All right. So with k-means, it's an iterative algorithm that sort of looks to partition your data set into k clusters. Now, k is defined by you as the user, and there are various steps to find a more optimal k value. How does this work? In essence, we would randomly initialize a k value. So we pick a centroid of choice, and then we would assign each observation to its nearest centroid. Cool. So from there, once we've got that assigned centroid, we'll then assign each observation. Now, this is a data point in the space that we would then look to see, does it match that K centroid? From there, we would update the clusters and centroids based on the assigned observation and then keep on moving forward. All right. And then we'll repeat steps 2 to 3 until we have convergence. And this basically means when the assignment no longer changes, or the centroids do not significantly move, right? So it's basically when everything comes to an end. Now, in order to evaluate a k-means cluster, we have a series of things that we can do. And the first one being the WCSS, and this is the within cluster sum of squares. It's a mathematical formula that we would, in essence, impute the various values that we have. And this is known as inertia. This metric is the measure of the sum distance between each distance point and its assigned centroid. So if you can imagine a dot in the middle of your scatter plot, we would go and calculate the distance between that plot and the centroid, and then add all of the ones around it. And the hopeful aim is that we have then the lowest WCSS score, which means these points are really compact, and this cluster then has very similar components. So the lower the score that you see, the better and more compact your cluster is. The higher the score basically means your cluster is more sparse, and the data points could be significantly different. So this is a simple example to basically create a random blob of data. And the goal is then we would basically get a bunch of data points that we can plot. We then can manually, in essence, calculate this WCSS score. To compute these different number of clusters that exist within our data set, we have to basically, like I said, find every single data point and then go and do the distance for each and every one to the centroid. So from here, we have a loop that will run through. This loop will run, in essence, 10 iterations because it starts at 1. We're then going to use the k-means algorithm, where the number of clusters we're going to test is 1. We're then going to test 2, 3, 4, 5, all the way to 11. So we'll go and calculate this over and over again. We're initializing it at a k++ score. We're obviously iterating this 300 times because our data set has 300 points. And sort of the n initializes at 10 and then just a random state. Now this value can change depending on what you choose. We're obviously going to next then fit it to k-means, and then we can calculate that WCSS score. And this is then what we'll produce. Now, as you said, the goal is to get a smaller number. So if we take and create 10 clusters, 0 clusters with the data set, that's the sort of score that we'll get. And if we create 2 clusters, 3 clusters, 4 clusters, and we go all the way through, and you'll notice that at some point, the gap between these numbers stops being drastic. So the first time we ever calculate this value, it's in the sort of 3,000 region. And at some point, you'll notice that it stops changing drastically. And when we start to get that, this is often known as sort of your convergence. So if you have to look, that's 1, 2, 3, 4. At sort of point 4 is when we're starting to see these clusters converging. Now, that's a mathematical way to do this evaluation. However, as data scientists, we tend to have some really good lazy ways to do this. We got the elbow method. Now, the elbow method is used to determine the optimal number of clusters, and this involves plotting the WCSS score against the number of clusters. So very similar to the above, it's just shown on a visual representation. So all the numbers you see on top is then mapped at point 1, 2, 3, 4, all the way through. And often when we talk about the elbow method, we're looking for the point of reflection, so the part that makes the elbow bend. And this basically means the WCS is decreasing less. And this indicates that the more clusters you add, no matter how many, the compactness will not change. So eventually, if we start to add 100 clusters, the score would not change drastically. And that's what we're looking to evaluate. So plotting the scores that we calculated above, we get the following. So there you'll see that first point of 2,800, the next point all the way through. And if we ask you what is the optimal point for when things pivot, an argument would be between 3 and 4 clusters is your optimal turning point. So this is how we try to then go and navigate this graph, and hopefully it makes a bit more sense. But when we're looking at your WCSS score, we're looking for the point at which this change stops being drastic, and that's known as the elbow method. All right, so that's the first sort of concept to understand and hopefully refresh on. The next thing we're going to move on is to transformations. So throughout your clustering, you've done this probably in regression, and at some points you might have also done it in classification, is the point of standardizing your data. Now, standardization is quite important for clustering as it allows you to condense certain information, right? So standard scaler is used to standardize the features before applying a k-means clustering, right? So it's before you try anything fancy, we try to reduce the values into a certain spatial awareness. The reason we do this is so that the data points are all confined and within similar playing fields, because if you're comparing millions to single-digit numbers, it does become quite confusing to interpret. The next thing we've got is something known as an inverse transformation. What often happens is that we scale our data, and very seldomly do people ever scale it back up, right? Or take it back to its original values. And this is then very important when we look to get to interpretability of our data set. So the inverse transform basically takes everything that was a scalar and transforms the cluster centers back to the original feature space. So if you can imagine your data set was in the hundreds, when we scale it down, it might be between 0 and 1. And then obviously once we've done all our calcs and we've got our new informational points, we can then say, great, instead of looking at our centroid as being 0.5 in the scaled version of the data set, we then scale that up to get the actual center point of the original data set. And this just makes things more readable for a user that understands the normal data set as opposed to your scaled version of it. Because obviously explaining to someone that's non-technical that this is the new data set can be quite tricky. So to do this, we're going to use the following data set for an example. You can obviously see the array. We've got a two-dimensional data set, 1, 2, 3, 4, 5, 6, all the way to 9, 10. Here we're going to implement a simple standard scalar, right? No adjustments to the actual parameters, and we would do a normal fit transform. This is similar to what you would have undergone when using regression models. Next is to apply your k-means cluster. So now we apply the k-means thing. We obviously specify in this case a cluster size of 2. We could be more thorough about this and go and work out the elbow method, but given the small size of the data set, you guys are welcome to just change these clusters and see a different output. Next is then to fit that to the scaled data set. Now, for those that are curious to see what would happen if you do not scale the data set, you're also welcome to simply put in the value of x into your k-means fit. This will change your observations quite drastically, so just keep that in mind. And the next thing we do is obviously we want to do the inverse transformation. So within the k-means parameter, there's something known as cluster centers. So once we've fitted this data set to each other, it will loop through, and then we would, in essence, get the centroids for each of those two clusters we've defined. And all that we're doing now is going to take that scalar model that we've defined earlier, and we're going to use the inverse transform method. This is then going to be applied to the center scaled. This can all be done in one line, but it does look a bit chaotic. So this is just to explain the difference between the two. And then we would have then the inverse and the normal data set. And how does this look on paper? So this is our original data set. As we can see, once we scale this data set, it moves between a more confined distribution. So the range is no longer from 1 to 10. The range is between negative 1.4 to positive 1.4. If you would like, you can control the bounds of your scalar by setting your min and max thresholds. But in this case, given we didn't define it, the model will choose its own optimal point for scaling this data set. Right. Now, once this is done, we then can find the cluster center. Now, in this case, it's not entirely difficult to find based on the fact that we've got a data set that lies between in the negative realm, and we've got one that's in the positive realms. And if you find the middle point between 0 and negative 1.4, that's obviously 0.70, and the other side of that is the sort of positive spectrum. You then got a different scale, so relatively easy to find, and this would then be the clustered centers. And then obviously this is not as interpretable when we're looking at our original data set. So what the scale or inverse scale does is converts that into its normal numerical data points. And we can basically visualize this as such. So I'm not going to look at the code now. If you, like I said, I will share this notebook, but you can just plug in your data points respectively for this. All that you'll notice here is I use the X data set. So before it is scaled, and we use the center originals. And then obviously the second plot is then that with the scale data set and your center scale. So that's the two different sort of features that you would need to update here, or variables better yet. And what we're getting is the following. So obviously it looks very similar because they're on the same grid space. But what you need to pay attention to is the Y and X scale. So you'll notice between the two, the original data set looks as such. And ideally, the whole point of scaling is just that you're reducing the size of the points and range of the data set. Once you scale it up or down, it should look identical. And that's the purpose of scaling. We're trying to just reduce the sort of magnitude of the data we're looking at. So in your eyes, you should see them as looking indifferent. And the whole point is that once you create this clustered algorithm with its K center point, we can then say, thank you very much. I'm going to then convert it back. So if someone asks you, what is the center or common centroid for your normal data set, you can come and reflect and say it's 2 and 3, all the way up to your second cluster, which is 7 and 8. So that's what this is all about, is making it more interpretable to your users. So if someone wants to know what is the center of all attention of your clusters, you're able then to give them the non-scaled value. Awesome. Hope that helps in terms of interpreting and reading this. And that is basically the cause and effects of the inverse scale. Right. All code, like I said, will be produced and shared with you for better interpretation, right? So in terms of just recapping, this piece of code is where we basically get your centers scaled and your centers original. So by default, you'll always get your centers scaled using the k-means.cluster centers, and you need to apply your scalar to flip it back to its normal original state. All right, so the scalar model is then what allows you to transform between the two centroid points. Great. Hope that makes sense. And we're going to move over into hierarchical clustering. Right. If you do have any questions along the way, I think chat is open, so you're welcome to stop me and I'm happy to try and explain it. Alternatively, I'll aggregate it towards the end. Right. Hierarchical clustering, right? It's a method for clustering analysis which seeks to iteratively merge smaller clusters into larger ones. And this is known as algorithmic. And then you've got the alternative approach, which is where we try to analyze clusters by splitting a larger cluster into smaller ones. So depending on the approach that you decide on, it's the way in which the data will segment itself. They're typically quite similar, and often the output or visual representation of these two algorithms look identical. So it's up to your data set in terms of how fast you want to see and produce outputs. Normally, the goal is to produce a dendrogram, and this is those tree-like diagrams that we worked on, and this illustrates the arrangement of clusters. Now, we did cover the theory behind it in terms of your y-axis. The higher up on the y-axis that you draw your horizontal line, the sort of less similar those fields are, and the lower you bring it, the more similar they are. Your key parameters when applying a hierarchical clustering algorithm is your linkage. This function is used to perform hierarchical clustering in different aggregations. We then have the method, which specifies how the distance between clusters is calculated. And lastly is the metric, and this parameter specifies the distance metric that we're going to use, whether Euclidean or so forth. So we've got another example to showcase this to you. So in this case, we're going to use Scrippy's clustering algorithm. We're importing linkage and dendrogram specifically and matplot. We're using the same X dataset from above. We've then defined our linkage as Z, and this is then what we're operating. It's your normal dataset that applies to linkage. We then have our method. In this case, we're using the single linkage method. And the metric that we're going to be using is Euclidean. Now, obviously, this data set is very vague, so the output is going to look quite boring, but let's go and evaluate. So in this point, if we look at the diagram itself, there are basically 1, 2, 3, 4, 5 distinct groups that have been formed, which is basically the 5 data points that are above. So they're distinctly all different and nothing sort of common between these numbers, which is what we would expect if we're analyzing this data. Now, to recap on linkage methods and what single was doing in this case, and if we had to choose a different parameter, which is what I'm encouraging you to do once you have this notebook, is look at how that dendrogram changes. Now, obviously, I'm not going to run all of them because it's simply changing the keyword from single to complete, average, award. You will then see a different output. So for single, it's the distance between the closest points of two clusters, right? That's then how we find a single linkage, and hence you saw the split looking quite vague. We then have complete linkage, and this is the distance between the furthest points of two clusters. Average linkage looks to get the average distance between all pairs of points in two clusters. And the last way that we have is Ward's method, which is used to minimize and increase in total within cluster variance. So try and run these different models. To simply try them, as mentioned, all that you would need to change is the method that you're applying. Changing the metric will have very minor effects on this data set, but you will see some changes on using different principles. So in terms of the methods that we use, it's linkage, method, and metric, and hopefully this explains how it's then implemented on an actual notebook. Right. Taking this a step further, right? So taking the same visualization, and I've expanded it for you, I'm going to show you the effect of applying different methods or linkage methods to the given cluster. So you obviously saw the one, which is quite vague and not exactly the best plot. Now we're going to compare all 5 different models that you can apply in terms of linkage. The only one that's not covered and not commonly used is centroid, but we thought it'd be a cool one to show you regardless. Right, so here is your plots, right? Your single linkage, as you would have noticed, it looks very much similar to the graph above, just slightly presented slightly more differently, but in the end, you'll notice it's just got 1, 2, 3, 4, 5, 6, right? So that's the values and how it splits. And then we've got your complete linkage, right? In that case, you can see a bit more of a segmentation occurring. Complete linkage and average linkage are again very similar in nature. You'll just notice that the gaps between the declarations, this one is at 10, where you first find the big break, where this is at 8, which means this is more similar than the complete linkage clusters. And then you can compare the other two again, centroid linkage and Ward linkage. And the main thing that we're comparing here to notice the difference in the algorithms is we're looking at the gap between the horizontal lines that we can draw. And generally, this data set is quite a poor one, as mentioned, but hopefully you can see that there is some cause and effects in terms of the grouping numbers that have happened in the bottom versus the y-axis that we're comparing, right? So just keep that in mind. It does shift algorithm to algorithm, and you as the data expert can decide if you want more distinctly defined cluster groups, or are you happy with it being more similar to one another? So take a moment to have a look at these visuals, and you as the data scientist choose on a case-by-case basis what is the best point. Now, again, these visuals are there to aid your decision in terms of defining the number of clusters you want. It's not there to be the absolute measure of a given cluster. Right. Perfect. Right, so again, as mentioned, code will be supplied. You can have a look and play around with it. But basically, these visuals are what you would generate if you came and changed the method above. This will just give you a zoomed in version on the given linkages that you're going to be testing out. Right. Moving over to cosine similarity, you guys should be getting more comfortable with this space in the case that you are now working with it in your recommender systems. We will be covering some tips and tricks afterwards to sort of discuss that given space. Now, calculating a user similarity using cosine similarity, it is necessary to transform the user item interaction matrix. This is basically the matrix that says what user has interacted with what item, and basically we then try to do it for all users in that space. And this is often the limitations of using cosine similarity in large data sets, is that that matrix expands exponentially, which is why we cannot run the algorithm of whatever it is that you're trying to run in terms of collaborative or content-based filtering for the current Kaggle dataset, because it is too large for the computer to run without paying for an advanced service. So in that case, the reason we do this is to get vectors. Now, vectors are what we are able to use to see how similar or dissimilar those things are. And if you remember the talk from last week, how we draw those lines and represent the space, this is then what's happening. Right. So taking that in, we then have the following formula. Cosine, right? That's why it's called cosine, is equal to the dot product of A multiplied by B. And that's are your two vectors that you're comparing. We then divide that by the magnitudes of A and B. And usually when we're talking about the magnitude, we're often looking at the distance, right? It's the value or size of it, right? And then we would do the calculation for it. And we can expand the calculation to the one you can see on the right. And note that this values at the bottom are always positive. So how would we calculate this manually for those that are looking to evaluate things, right? For a user represented by vectors u, right, is the sort of A in this case. They've got the following combination of 4, 0, 0, 5, 1. The other vector that they have is u2, which is then 5, 5, 4, 0, 0. So those are the two parts that we've basically got for our matrix. So firstly, we would calculate the dot product, which is basically multiplying every value with every alternative value. So 4 multiplied by 5, 0 multiplied by 5, 0 multiplied by 4, 5 multiplied by 0, and 1 multiplied by 0. And then we basically get a value for that, and that would then give us our dot product. So our dot product, or the top of that equation, is going to be equal to 20. In this case, a lot of those values canceled out. Magnitude is then obviously calculating the size of those vectors, right? So in this case, there is a formula that you can follow, right? So we aggregate and plus minus all the way through. And eventually we will get for A, right, is 42. And for B is 66. So now we've got the value of 20, 42, and 46. And we would plug this into our formula, right? So the top is basically going to be 20 divided by basically 42 and 66. And that's how we calculate. You then do the divisions and you will then get the value of your cosine similarity score. So that's in essence how we would go and calculate these things, right? So it's very mathematical, but in essence, all that we're doing is calculating A, the dot product of that equation, and then looking at the magnitude of A and B. Now, the formulas are going to be included for you. It does render a little bit differently when you have it on Jupyter notebooks. So I'd recommend opening this notebook there for ease of visualizations. Colab was not allowing for very happy formatting. All right, but if you do want, I've also included a link to an image of this given calculation. Right. Cool. So that's cosines, right? It's the formula needed to be explained. Hopefully this will tie in later when you do open that given exam question. We spoke about standardization. I'm sort of just going to be building up a bit more about this. So with standardization, the steps for standardization involves initializing your scalar. We then fit and transform our x values, which then returns our x scaled values that we can then plug into k-means. The fit component basically will compute the mean and standard deviation of every single feature we have, which is basically your columns. Transform part basically standardizes the dataset using these statistics of mean and standard deviation. After the step, x scaled will have a mean of 0 and a standard deviation of 1 for each feature. So that is what transform is doing. You can imagine in a normal data set, every single column has a different mean and a different standardization or standard deviation. What we're looking to do with scalar is to reduce that so they all have a mean of 0 and a standard deviation of 1. So if you ever calculate or aggregate the values or means and standard deviation of any scaled data set that you have not customized, you should receive the mean of 0 and a standard deviation of 1, regardless of how you compute it, whether your scale is between -5 and 5, or -1 and 1, or -1.4 and 1.4, as we saw above. When you do the calculation for that given data set, you should always see a mean of 0 and a standard deviation of 1. Right. The clustering model we're going to show below is that of the algorithmic clustering, right? So obviously we've shown you different ones. We're then using the linkage of average, right? And then we're going to apply and initialize our cluster. So looking at the code for this, same data set that we've had above, we're going to use our scalar that we've initialized. We're then going to use the fit and transform to adjust that given data set above. And then we're going to apply our model to it to get the following. Once this is applied, these are the steps. The key thing to note that you can control is the number of clusters, which can be optimized using the elbow method. And then your linkage will affect the clustering specifications as we saw above. So you'll either get more defined clusters or more loosely defined clusters, depending on the linkage type you choose, with the single linkage being the most neutral of the two, in the sense that it has very low difference thresholds between each individual cluster. Right. To obviously go further than this, we can go and visualize this data set if we want, but the visualizations would be the exact same as what we've done above in terms of plotting the graphs as shown here. The only next step is to iterate over the linkage and produce the denogram. So that's why we're not showing the code again. I would like you to adapt some of it for yourself. Right, but this is how you would apply a different model in the sense, and the only thing that's changed is the model we're using. So the decision of whether we're trying to use the default hierarchical clustering or if we're using the alternative, which is your, now my words have left me. Good thing we've got a notebook here. Your divisive approach, right? So by default, you'll tend to use the algorithmic, but you can switch and use the divisive, right? So to change that, it'll just be a different import from sklearn's clustering algorithm set, right? Next up, that's important for you to know is how clustering works in geospatial analysis. So three main components of geospatial analysis is for spatial grouping. The clustering algorithm in geospatial analysis allows you to point together or group points together based on their physical proximity in a geographic space, right? So not a normal data set array. This is something that is bound by geography, right? Pattern identification. What happens is that we are then allowed to identify clusters or concentration of points that exhibit smaller spatial characteristics, such as density, which is how close they are and how tightly packed, or proximity, which is how the distance between points. The application for using geospatial analysis is one that's used for urban planning. So often as an engineer, you would need to see the cause and effects of putting a town hall somewhere. Now, or townhouses, or if we're going to put high-rise apartments. Now, this is something you should be doing, but often is ignored by a lot of planners because once the money hits their account, they don't follow all these processes. But that is why we tend to have urban congestion where roads are overpopulated. It's because poor urban planning of how we are clustering and grouping people has not been done optimally. And by the time you try to do that, the infrastructure is built up too far to allow you to expand roads and so forth. And that is why one of the solutions now for updating and improving highways or roads is to go underground because it's untouched land, because we cannot move buildings and so forth. Next is for epidemiology, natural resource management in the sense of farming. It's used quite well to see where crops should be best placed and used. Next is in retail to identify spatial patterns like disease, outbreaks, urban development hotspots, customer clusters for targeted marketing. So often when you're looking at certain things like Amazon that are looking where to set up their next warehouse, they would use geospatial analysis to see which country has a market for them, has the affordability, has the space for them to set up shop so that they can then implement their own retail hub. Now, they won't just go to a country that has no infrastructure, has no demand, or is stricken by a desert because they can't then get their staff to certain places. So highly unlikely are you going to see the Amazon in the middle of the Atlantic or Arctic sort of continent, right? Everyone would just ignore it because there's no demand. And they are able to use these algorithms to cluster, group people, work out financial spends, and move forward. So, welcome to GeoPandas, a package that you can install similar to how you install pandas, except this case it's pd.geopandas. The main difference between GeoPandas and data frames is data frames are general purpose data structures for tabular data handling in pandas, right? So you can only use the pandas module to interact with data frames. The geodata frame extends on data frame functionality, and this allows you to use spatial data types. So we're looking at coordinates and stuff with preserving that information. You can also use polygons and so forth to storing information beyond the space of a normal data set. And you can do some advanced operations in that space. And this makes it really good for geospatial analysis, which is what we spoke of above, and integration with GIS workflows, right? So this is a really useful tool for mapping and land surveying that often is used in most utility companies. Now, the three things that it's good for doing, as we said, is spatial data handling. So it can store and manipulate spatial data such as points, lines, polygons, and multi-geometries, right? And this is stuff like multi-points and multi-polygons. Next is geometric operations. So the maths that we spoke about, it provides methods of geometric operations like area that can be calculated, distance between points, buffer points, as well as spatial joints and connections. Next is it integrates lastly with GIS, and this is designed for integration with the Geographic Information System. And the libraries that allow you to then connect GeoPandas is stuff like Shapely, which allows you to put polygons onto a visual representation for you, and Fiona. So these are really good visualization tools to showcase GeoPandas data frames. Moving on to DBSCAN, another one of our clustering algorithms quite popularly used. In this case, we're going to use the following data set. These are coordinates on the following space. And the aim is that we want to do a scan to see how these coordinates map to each other, right? They are different, right? While there are minute changes, this is quite significant in a geospatial space. So we can run our DBSCAN with our EPS value, which we've shown you how to calculate when we did our practical showcase. And we've got our minimum samples. We're going to fit it to our coordinates data set and then get the labels. Now, what this means when we produce or run the following tests, right? This is based on the Athena question. The points are divided into clusters with at least one noise point. That is the observation that is seen here, right? So every single point is -1, -1, -1. And the reason behind this is due to it not being close to any core points of our epsilon value, right? So the reason behind receiving -1, -1 as our labels is due to it not being close to the core points that we've defined as our EPS values. So that is what's going on in this given visual, or not visual, but this given analysis, is that you are looking to evaluate those numbers. So once you run it on Athena, you will get the similar output to me, and the interpretation of these results is the further away it is from zero, the more noise you have. There are different interpretations based on the data you put in above, and you just need to observe the variance between those points. Right. Gaussian models, a very big part in terms of probabilistic modeling, and a very powerful model when done right for gambling, is Gaussian models, right? So the shape of a Gaussian distribution is one that makes it quite popular. we often refer to something known as a covariance matrix. And this determines the shape of the elliptical contours. So you'll notice that if you decide to plot a GMM, you will basically try to plot the shapes or these oval shapes onto your data sets, which allow you then to see various information such as the spread of your data set, all the way through to your variance of it. And the reason what it tries to do is to show you how well your data is spread out, which is around the mean of each component along different dimensions or features. From a modeling perspective, we've got the variability that it shows. So the different covariance matrices allow GMM models to show you different variances and correlation amongst features. So when we're unsure about how features communicate with each other because they aren't labeled or unknown, a Gaussian model is really good for finding similarities and correlations between columns that are either poorly marked or poorly understood. And the next thing that we look at is the diagonal of the covariance matrix. This assumes that features are independent, while a full covariance matrix captures correlation amongst features. The real advantages of using these Gaussian models is firstly the flexible clustering shapes. We can model the ellipse to get more accurate dimensions and shapes around our data set, and it handles different orientations and spread of your data with certain diagrams and use cases such as k-means, where we are limited to a circle, and circles can't be turned because circles are equal on all sides. The shape of an oval allows for much more customizability. We can choose how narrow we want it, how elongated. We can also tilt and manipulate that oval to produce different sorts of segments. Step point 2 of the advantage is its probabilistic assignment. So it provides soft clustering with probabilities for each point belonging to multiple clusters. So it doesn't just group it, it will tell you that there is a 10% chance it belongs to cluster A, or a 30% it belongs to 2. And this allows for very advanced interpretability. So when you are saying that a customer belongs to cluster 2, what Gaussian is able to say is, well, there is a probability that it belongs somewhere else, and this is the percentage of that probability. So really useful for explainability. And with using these ovals, it allows for overlapping. Given the fact that every observation is a probability of belonging to a cluster and not held to an absolute value, we're then able to find optimal overlapping points due to the flexibility of the probabilities that are going in. And last advantage of it is handling variability. So this supports clusters with different variance and covariance. And lastly, it's suitable for very complex data sets with varying cluster characteristics. So to show you an example of this, we've got a data set. Note that this data set will change every time you choose to run this notebook, so keep that in mind. We're looking to only have 2 components, and we've got the covariance type to full. This is another thing that you can adjust to see different effects of the given model. We then are going to extract the means and covariance values, and we then produce the following output. So these are covariance means and the covariance matrix. And as we said, we compare the diagonals to then see and evaluate the data set itself. Now, this is not the most useful visualization to understand Gaussian models. The best thing is to take that same data set and get a plot. Now, there are multiple ways to do it, right? In this case, we're going to take another synthetic data set because, as I mentioned, it updates and changes based on every iteration. The same thing applies, and the reason behind me showing you a different data set is to show you that these clusters will differ every time. We're then going to print out our labels and then put it onto a plot, and this is the following output. So we defined very strictly 2 distinct cluster groups. We could take it a step further, but you can imagine that looking at this current visualization, it is highly unlikely that there is a new cluster that's going to form. But I highly encourage you to change that value to 4 and 3 and see what your observations are, right? Obviously, because it's a very simple data set and a constrained data set, it's very easy to control and define the clusters. More computational data sets that are more complex and contain more variance will then receive different visual outputs. All right, so useful for clustering. And if you look at it, it gives you quite smooth, definitive shapes for these clusters. Now, to show you an alternative effect of sort of the Gaussian models, is understanding what was actually shown. So with this, if you can imagine putting an oval around these, a GMM, we look at the width and orientation. So the width often refers to the spread of the data. So the covariance matrix determines how spread out the data points are around the mean of the Gaussian components. And this is why we produced or printed these out. So these means correlate very closely to the covariance scores that come out. The larger values in a covariance matrix indicate that the data points are more spread out, resulting in a wider Gaussian distribution. The orientation of the given ovals, which you cannot see in that visual, the covariance matrix allows us then to define the orientation and points. It's basically the tilt of that given oval. The off-diagonal elements of a covariance matrix capture the correlation between different dimensions, so column 1, column 2 in this case. And this affects the tilt or the orientation. So depending on how it's skewed, will tell you how well the data is correlated with each other. If they both tilted the same direction, you can imagine that there's a strong correlation between the two. If they split, it means that they are differently correlated. So to show you this in a different format, right? Again, this data set is different to the one above. We run the same thing to show you the cause and effect of this. And in this case, I'm going to actually plot the Gaussian components and eigenvalues. So you'll notice the means change slightly, obviously very similar because of the data set itself. And this is the cause and effect of that. So now this is a very different data set to the one above. The one above tells you that there are two distinct clusters, right? This one also should tell you that there are two distinct clusters, but it's a bit more difficult to interpret. But what we're looking to see in this given point is that we do have, in fact, two distinguished data sets. And the orientation and flip of it tells you how dissimilar or similar these values are. Right, so that is the usefulness of this visual, is you're basically interpreting the width, right, of this oval, and then you're interpreting how that oval is slanted. And as we said, if they're slanted in the same direction, they're similar. They're slanted in opposing directions, they are different. And obviously, the bigger the tilt, the more different they are. And then the size of this given oval then indicates basically the spread of the data. So this is then how we interpret these results. And as you look to evaluate it, look at the size of that oval and how it's orientated. All right. Moving on to PCA, right? So PCA is most commonly used for unsupervised learning, right? So it's used to reduce dimensionality of data, identify patterns, and simplify data visualizations without relying on labeled outputs, right? So the whole point of it is for unsupervised, where we don't have label. However, for supervised learning, we can use PCA, but it's not a supervised learning technique, right? It's not something you will commonly apply. So if someone says, can you use it for supervised learning? The answer is partially yes, but it's not the primary use. Its primary use is purely for unsupervised learning. It can be used for pre-processing step in a supervised learning task. So if you have a 100-column data set and you're not sure about the features you want, you can use PCA to reduce that data set and then go and apply a normal regression model or classification model. But this is very seldomly done, as it is more suitable for things where there is unlabeled data sets for reduction of data. To show you what this looks like, PCA, right? We're referring to, or going to extract the X data set that we've used above and created several times. And very similar to most of the things above, you should see two distinguished groups of data, right? You shouldn't see anything more because this X data set is the same, right? So more often than not, most of these unsupervised things will all speak to one another, right? So if you do a hierarchical clustering and you do a k-means clustering, ideally, if it's done right, they should come to very similar conclusions, right? So again, PCA simply is just to break down the data set and is, again, more often used for unsupervised and very seldomly used for a supervised learning model, because to group and cluster your columns and features isn't as important. While feature reduction is important, clustering and grouping them is not as important when you're doing regression modeling and classification modeling. All right. Eigenvalues. You would have heard this come up at different points, and this is because it ties in with PCA. Again, we have another random data set that we're generating, and we would then be able to figure out what is the best eigenvalue for it. Now, the following plot will give different points of eigen, and we're looking for significant changes in the given data set. So whenever this graph does something random, right? At this point, the most obvious detour from this graph is that of 2. So very similar to the elbow method, except in this case, it won't always be an elbow. It's just going to be an deviating point in your data set. This then will tell you how many sort of features or groupings you have. So very similar to that of your k-means elbow plot. This then shows you the sort of eigenvalue that was used before your principal component drastically shifted. Obviously, you can choose another value, but as you can see at some point, it just becomes very standardized. So we're looking for the first significant hiccup in this given plot. So if ever you see a scree plot again, you're looking for a deviation in that line that looks significant. Sometimes you will see multiple and use the first dink that you see, right? So imagine it as a car where the first dent that you see is then the recommended eigenvalue for your PCA plots and visualizations. And this will then help with your feature reduction. Cool. Looking at those given PCA points for an alternative data set, right? If we take a data set, as you said, we're trying to reduce data sets. So looking at this given data set that we have, it's a 3-dimensional data set, right? 1, 2, 3, and that's the values for each of these data points. As we said, PCA is there to reduce features. So when we run it, something else will output. In this case, you'll notice that 2 dimensions have formed. Negative 7.7 and 0 for pretty much every other data point. And we basically reduced our entire data set from having a, 3 by 4 matrix to now simply being a 2 by 4 matrix. So we've reduced an entire feature to nothing and combined and aggregated some. So this is useful when you're trying to cut down columns, but what it's not useful for is classification and regression, where combining certain columns do not make sense, right? Certain features should be left independently and should rather be joined through feature engineering than that of principal component analysis. So be very wary about using PCA for any supervised learning algorithm. While it can be used and you can see good results depending on the data set, it can confuse the user in terms of interpreting what's happening. But as we showed before, you can change and pivot these data points back to normal, but it's not always trustworthy. All right. So that is then some of the key concepts you need to know for this given or your upcoming exam. As mentioned, I will share the notebook with you. Anyone with link can view it. Great. And this will go into chat. And now I'm going to switch over to sort of just opening up the poll. Maybe just, are you prepared for the classification or unsupervised exam is pretty much the poll for today. Hopefully you had a good recap and refresher on some of the unsupervised terms. Notebook is available. And I'm going to move over to some updates and announcements or Q&A, and then I'll move forward. Right, so Q&A, I'm going to start with Zoom and I'll move over into Slido. Right, so firstly, how is the movie recommender system graded? I saw this on both sides. So basically, we will be taking a scrape of the data from Kaggle. So we'll log in all those that submitted. We will then take that metrics over, and we will be awarding on a basically a piecewise linear scale. Top candidate will get the highest mark, but you do have to achieve a minimum. And the reason we're saying that you have to achieve a certain minimum is because we achieved that in the starter notebook. So achieving the exact same output as us will give you a default mark of 50%, right? So that's how you would be graded, is if you get the same as us, you get 50%. As you gradually improve that score, you will get a higher mark. And then we set sort of the threshold that if you're able to beat the scoring metric, which in this case I think was 0.75, if I'm not mistaken. Let me just look at this very quickly before I give you that number. So if you are able to achieve a score of, give me half a second to get there, of sort of 0.95 to 0.75 as your root mean squared error, if you can beat 0.7, right, you will get 100% for this component. These marks will be added in a separate section to Athena, so it will not affect your overall course mark. But we do highly encourage you to attempt this to get some understanding on both Kaggle, which is a very important tool for practicing data science, modeling, and good exposure to real-world data sets, and get familiarity with the sort of real important space, right? So that's what's happening in that front. Cool. Next question that we have. Right. How is this going to be graded? I think I've covered that, right? You will get a rank on the leaderboard, so don't worry about competing against your peers. You're competing against an RMSE score. Yeah, RMSE score. Right. Next, do you know how many students are in total on track? Currently on track, there are 90% of you all on track. Yeah, so based on the original cohort, currently 90% are still active in the given course. It's quite a big number. If you are feeling overwhelmed, note you're not alone. Everyone is struggling through it, but you will get better. Right. Next one from Ishmael. Is there a minimum score to pass the Kaggle competition? As mentioned, as long as you submit the equivalent notebook to us, you will get 50%. So we're mainly just checking that you're able to run a notebook, make a submission is the first thing, because it's an important platform to get familiar with. All right. Next, on the Kaggle project, when running code, I get an error run out of memory. The reason behind this is you are using too large of a data set. We've got some tips and tricks we'll cover soon, but basically you're going to have any issue if you try to run the whole data set, and I'll cover that in a short second once I cover the tips and tricks. Right. Next up is how do we determine the scalar used between min-max and standard scalar? What characteristics of the dataset do you need to know? So typically by default, I've always used the normal standard scalar and let it automatically adjust, right? So keep that in mind. You can just let it run on its own and it does a significant job in doing it very well for you. The way to do it manually is to extensively run EDA on your notebook and find what is the lowest min and max range that you can implement onto the data set without causing any skewness to the data set. So I know it sounds quite weird, but that's in essence then how you would go through it. It's a very long process and often not recommended to do unless you're trying to optimize a model from 95% to 96 is when I would say I'd recommend trying to optimize that given parameter. All right. Cool. Kaggle, yes, to run it, reduce the data set. We'll get to that in a second. The goal of the movie recommended system is not optional, right? It is a compulsory thing for you to do. So please, you've got the starter notebook, is make sure you get a submission in. Cool. Submission for Kaggle is on Sunday, whereas your final exam is due on Monday. And obviously you have had a bit of time for the Kaggle competition, which is why the exam due date is on Monday. All right. Next is if you're getting any errors on Kaggle when trying to submit, the reason behind getting the error is because you probably got a running code error in your notebook. So often the notebook can't run end to end easily without it causing any errors or runtime errors. In that case, you are able to, there's a piece of code that's available on Kaggle. If you Google it, it's how to get a hyperlink for your data set. And basically you can run that code to extract the CSV. So you don't have to run the code to get the output. You can simply run a cell and it gives you the option to download the CSV in the next cell. So that way you can avoid submitting the movie recommender system notebook and you can just submit a CSV as opposed to the whole notebook for the competition, because that does get a bit more finicky. All right. And then how do I upload CSVs to Google Colab? I'm going to recommend you ask that on AnswerBase so we can send some screenshots, because I won't be able to show you that right now. All right. Next, if you don't, will you be dropped if you don't complete the Kaggle competition? We are nice people, but again, we do recommend that you attempt this to get the exposure. So while we won't drop you, the Kaggle competition will be open and you can submit. The whole point is to get you practicing on time, under pressure, and experiencing a real competition and data set. All right. Cool. And then moving over to the other spaces or questions. It looks like everything else is fine. There is one on data analytics, right? So, oh, never mind. Yeah, what is the difference between data science and data analytics? Data analytics, you can imagine to be more business centered in the sense of presenting data, visualizing data, and telling a story. Whereas data science is more hardcore statistics and analytics. So it's around how do we future forecast, how do we optimize systems, and that's where data science is. In the real world, it's the more advanced version of analytics and processing, right? But in most job titles, they are quite similar, right? So tips for Kaggle competition. First note, the whole data set cannot be used, right? Unless you're spending money, you will never be able to use the whole data set. Some viable options that we recommend for you. The first one is partition your data set and combining. So one of the methods that you can use, and you do need to start quite early with it, is obviously when you're training the data set, you've trained it on a subset, is then keep training on multiple variations of that, and then eventually combining those models into one holistic model. It is a bit more tricky to implement, but it can be done. Next up, for those like me that have had a lower grade computer when they were studying, right? I had a Samsung family computer with no RAM other than a 4 gig RAM. I had to connect to a cloud computing system. So the likes of AWS, you can then connect your Jupyter notebooks to that. Now, this is a way to go. It's not the most or the best possible solution. The best possible options that we are going to recommend to you is that of Kaggle and Google Colab's accelerators. They are free for a certain amount of time, but you do need to have an active internet connection. You also need to ensure that your data set is reasonable, right? To start small, once you've got a successful iteration, upgrade it later. But do not try and run the whole data set on these accelerators. It will still crash. This is a very large data set and computationally is expensive, which is why most of the time your notebooks are crashing. The other one and the options we decided to share, just so that you know, is their expensive options. You can either pay for Colab Pro, which allows you to a whole PC of your own that will run this data set without even trying. It is very expensive, which we do not recommend. The second one, which we also don't recommend, is you can connect to Databricks and run an ML model through Azure. This again will achieve the results you want of running the whole data set very quickly, very effortlessly, but it does cost money. So both are not recommended, but for those that are crazy, you can do it. But note, running the data set on the whole data set does not guarantee, a better model, right? And the significant change between that is not significant. So please do not be spending money to beat Kaggle scores. Keep things simple. All right. Next up, sort of announcements and updates. I think I'm taking it today. All right, your Kaggle movie recommendation project closes Sunday, the 23rd of June. Your final exam for the unsupervised learning exam MCQ is 39 questions and is due on the 24th, right? So please keep track of those events and ensure you're getting your submissions. It is a long exam, so make sure you get through it. There is a mix of multiple choice, 4-choice questions and true and false. So some might go quite quickly, and use your resources. There is a webinar watch party for today's webinar tomorrow at 2 p.m. And your next webinar is on Thursday, right? Which is going to be run by Buhari. And remember to engage in your study groups and discussions sessions this week. And the last reminder from our side is your next FIS milestone is due on Saturday, the 23rd of June. So again, keep an eye on those deadlines to ensure you are not disappointed by missing those important milestones. All right, and the last announcement I have for you, and I'm sorry, what? Oh, yeah, wait, sorry. Support channels. Answerbase is there for your technical support. Layer, which is there for your any issues that you might be having or AI assistance that you might require. And for your day-to-day interactions, do not forget about your community platform. Now, slide order's changed, but I do need to make an announcement because this is officially my last webinar for the program. I have taken over a new role and will be leaving the space, and I will be leaving you in the very capable hands of the team that remains, right? So a lot of the stuff you guys have a very good foundation of. You're moving over into the cloud computing sprint, which is more of a data engineer's professional space. I will be amongst the chats and I will be in the sort of webinars along the way, sort of for the next month. But come 1st July, I will be taking over a new opportunity. The details will be shared at some point in time, but for anyone that was curious of how the interview tips and tricks go, I think I've got some good tips on that. So follow those webinars closely. But it is exciting opportunities. It is going on to some big, cool stuff that I will be sharing along the way on LinkedIn. So if you are curious to know what craziness I get up to, you can follow me there, but I'm not advocating for you following my boring story. All right, so thank you all for a very memorable experience. It's been an honor and privilege to teach you and share the knowledge that I've had all through the way, right? And yeah, sort of tot ziens and on to the next. Yeah, that is all for today. We will be in touch. I have an open book policy, so you're welcome to come and chat. And yeah, we will see you all on the flip side of things. But as of now, thank you so much for an incredible journey. I wish you all the best in your own individual journeys on your path to success, and hope to see some good LinkedIn updates from all of you as you sort of progress in this world of data. Thank you, and we'll see you on Thursday. Cheers for now, and bye.
No, they throw bad vibes. When the money day, that is where I'm at. Anyhow it be, I dey play my part.
Maestro Sugar. I let the water touch my knee. Can't let these people get to me. I know I never drink. I'm mixing with that NSC. I need my enemies to cease. I know they wanna find a crease. God they see in me. Hallelujah. Give me the walk, but it's heavy on my palms. I watch my walk, cause it's heavy on your heart. You hit my line, but I'm talking to my moms. And when it's time, I'll be talking up with God.
When the money day, that is where I'm at. Anyhow it be, I dey play my part. Iki kokoro, magumi, doju, mi o fall.
No, they throw bad vibes.
When the money day, that is where I'm at. Anyhow it be,
I dey play my part.
Iki kokoro, magumi, doju, mi o fall.
I go dance for you, Michael Jackson. Mama always say, son, have mercy on me. The angels never forsake me. Hallelujah, more any cage. Promise to play my part. Sometimes I pray and fast. 7 days and nights, forever delight. Son of Amdallah. Hold on, yeah, you know I was a rasta. Play them Kiga. Mama logo die. See my flows fire. Don't get throw bad vibes.
When the money day, that is where I'm at. Anyhow it be, I dey play my part.
Igi gogoro, mago me loju me o fall. No they throw bad parts. When the money day, that is where I'm at. Anyhow it be, I dey play my part. Igi gogoro, mago me loju me o fall. No fall.
I'm leading a life that can clean me from my passion. Burn up this money and live it in my ashes. The Lord is blessing, I'll see if I can match it. If something's coming, I see it in my lashes. Never stubborn when the red light flashes. To be real, I'm still eating off my last hit.
No, they throw my guns. When the money day, that is where I'm at. Anyhow you be, I dey play my part. Igi gogoro, mago me loju me o fall.
No they throw bad parts. When the money day, that is where I'm at. Anyhow you be, I dey play my